Okay. Okay. So I think we can start first. Let's. I know a few people relate, so like let's just start first now. It's okay. Okay. Uh, so like jumping straight into it, I think SR is like something that might be a little bit more foreign to you guys, and it's foreign to everybody when you learn it for the first time. But I just want to start with a short introduction of why you should bother learning SR properly, even though it might seem like it's detached from the rest of physics or the rest of the IFO or SFO syllabus as a whole. So this is just from like statistics. So uh consistently there has been at least one SR question from SFO 2016 to 2024. You can see, so I think this is a trend here that is quite obvious. I think quite sure to say that there will be SR this year, at least one SR problem. I think it should be one because most of the years it's exactly one. But even if there's one problem, this will make up around 10 marks out of like 80 to 100 marks of your paper. So this is a 10 marks that you definitely should not throw away, even though it's tempting to just not learn this topic and then just throw away the marks and get all the other marks. But I don't think this is safe in my opinion. So I would still want to encourage you guys to learn SR properly, even though it's quite foreign, it might be quite daunting, but I guess that's what this lesson's for. Yeah. So please don't throw this away. Okay. Okay. So I'm going to jump straight into it. There's a whole section here on Galilean relativity. I'm going to skip this because this is your basic uh relative stuff that you have learned from kinematics and dynamics. This is just the normal stuff. So there isn't much to it. Like it's just adding, for instance, adding velocities the normal way you do, like algebraically. And yeah, it's not too deep. So you can read this on yourself. The first thing I'll jump into is actually these two principles. So these are by Einstein. The first one is, okay, the first one might not be as important. It basically just says that there's no one special inertial frame of reference that is correct or the best frame that you can use. Basically, you can go into any inertial frame of reference, the laws of physics must still hold. And this kind of makes sense because you can't have a universe that's working on only one special frame of reference. Then anyone else in any other frame of reference would not, like physics would not function properly for them. And that's not what we see in daily life. The second one is more important. Basically, it's just saying C is constant in all frames. And yeah, so the speed of light is the universal speed limit. It's the universal speed limit and it's constant in all frames. So there's a, there's a bit more stuff here. I think these you can also read on your own. The
Wait,
thing,
huh? Are you sure we are going to MRT? No, no,
uh,
I'm showing. Wait, it's closed.
I think,
What the hell? The lawsuit is closed.
I think someone's unmuted. Okay, never mind. Okay, so first important like quantitative concept is the invariant interval. So this is just how it's defined. Basically, if you know this alone, you can solve all relativistic kinematics problems technically, but it's not the best way to do it. But this is a very important tool for you to check your working and check your answers, as you will see so in a later example. So just remember how it's defined. Uh, of course, these are all infinitesimals, but you can generalize them to like you can write these instead lah. Yeah. So yeah, that's that. Okay. Then there are a few thought experiments here that I go through, but I think the derivation of all these relativistic results are not as important. It's most important for you to know the result and know how to apply the result correctly, because even applying the result correctly might be a bit difficult at first. So the derivation here, I'm going to skip through. I'm just going to focus on this result, which is equation 10. So This is what we call time dilation. It's dilation because time is getting longer. Time is getting longer because gamma is more than one. So TB is greater than TA. So it's quite important to know this formula. But beyond knowing this formula, you need to know how to apply this formula, right? So the thing here is that TA is your what we call the proper time, and is what we call the dilated time. The dilated time is longer than the proper time. And in this case, the B and A are okay, B is the person on the ground who's seeing the train, yeah, the train moving. Then A is the person on the train. So A is moving together with the train. So A is in the train frame and B is in the ground frame. Who and you see the train moving. So what's happening here? So they are both observers here are seeing the same two events, right? Event one is okay, I'm gonna write out. Event one, light leaves the source. Event two, light comes back to the source. And both observers are seeing this, the same two events, but they're seeing different time intervals for these events, precisely because they're in different reference frames and they're moving at different speeds. So here, TA is the proper time, and it's defined this way because this is the shortest possible time interval. And this happens when the two events happen at the same position. And yeah, I've defined the two events here. So clearly you can see in this frame, the two events here happen at the same position, which is at the center of the train, because you're in the train frame, so the position is the same. But for B, because it sees the train moving, so it has moved some distance here, and hence these two events are not at the same position, which is why B sees the dilated time and A sees the proper time between the two events. So the other tricky thing here is that sometimes there's not even one frame that's observing the proper time. So what this means is that you cannot always assume equation 10 will work. Equation 10 only works if one of the time intervals in this equation is a proper time. There are certain scenarios where none of the frames see two events happening at the same position. In that case, you can't use equation 10, and you have to use a more generalized version, which is part of the Lorentz transformations. We'll go through that later. So this is proper time. If there's the most important thing that you should take away from this is which one is the proper time. This is the most important thing you should take away from this. Once you figure out what's the proper time, the rest of it is should be quite simple because you're just applying the equation. So, okay, I will ask if there are any questions at this point because I think this up to this point can be quite confusing, really. Okay, how do you know none of the events are in proper time? So events are only in proper time if they are at the same position. It is possible I mean, it is quite possible that you have a situation where you have another observer. Okay, let's say observer A doesn't exist. Okay, let's say observer A doesn't exist. Let's say you have some other observer and he's moving. Okay, let's say this observer is moving this way at V instead. Then clearly this observer, let's call him C, right? He's not going to see the two events at the same position. And if you only consider observers B and C, but yeah, this is relative to ground to be completely precise. Okay, so if only observers B and C exist, their two times are not related by the time dilation formula because none of them are seeing the proper time. None of them are seeing in the frame where the two events are at the same position. So this is one kind of trick that is like a tricky part that you need to be familiar with. Yeah. So that's how you see. Not simultaneous. It has to be at the same position. So yeah, position and simultaneous are different things. Yep. Okay. Okay, can. Okay. Let me check if there are any more questions. Okay, there are no more questions. Okay, then I'll go on to length contraction. This one should be hopefully easier to understand than time dilation, but they are kind of talking about the same thing if you realize. So there's another experiment here. I won't go through it. You can read it on your own. And I will again emphasize the final result, which is this. So what does this mean? This means that uh any this means that L prime here, L prime is greater than L because gamma is greater than one or greater than or equal to one, which means this L prime here is the longest possible length you can measure. And we define this as the proper length. Proper length occurs in the frame whereby the object is at rest. So you can see here in this experiment, the L prime is here, right? And A is in the train spring. Obviously, if A is moving the train, then A will see the train at rest. So A will measure L prime, and L prime is the proper length of the train. This is also the longest possible length of the train that you can measure. So you can see in the picture here, the L is shorter than L prime because other observers who are seeing the train move will measure a shorter length of the train, which is called length contraction. So again, the again, I think the derivation is not as important. It's just important for you to know which one is the proper length, and then from there you can figure out all the contracted lengths. So, uh, yeah, know how to identify proper length. So there's a slight difference in the way proper length and proper time are defined. Proper length is in the rest frame of the object. Proper time is in a frame where the two events are at the same position. So you just need to be a bit careful about the definitions. Okay, then there's this thing here, which states that time dilation and length contraction are equivalent. What this means is that I do not see any, okay, from everything that I've done so far, there shouldn't be a situation where you have to use both time dilation and length contraction at the same time to figure out something. If you find yourself doing that, then you are probably doing something wrong because that will kind of double count factors of gamma. So actually, you realize that SR is just about factors of gamma. So it's important that you don't double count this, which means it's either you use length contraction or time dilation. Example 1/1 will show this to you. And another thing here, length contraction only applies parallel to the direction of motion. So if you see okay, if you see a rectangle moving this way, then this length L is not contracted, and only this length big L is contracted. Yeah. So this is just something you need to be careful about. Any direction that's not parallel to the direction of motion is not contracted. Okay. So that's on length contraction. Again, I'll stop here for a bit if there are any questions on length contraction. Okay, so if there are no questions on this, example 1/1 is quite a good example to illustrate length contraction and time dilation. So it asks you to solve this problem using two different methods, either time dilation or length contraction, which kind of shows you that these two are mutually exclusive. So you can, so this one is kind of worked out in quite a large detail. Uh, yeah, I guess you learn this in the next chapter, but it's good to know. And you can see how it's like worked out step by step. So basically, there's a lot of justification here on why some frame sees the dilated time, why some frame sees the proper time, why some frame sees the proper length, why some frame sees the contracted length. this is the most important part that you need to understand. So you can identify the frames correctly. Otherwise, if you identify the frame wrongly, then your gamma is going to be at the wrong place. So you can see how here the muon burst and decay, right, of the muon, it obviously happens at the same position in the muon frame because that's where the origin of this frame is, at the muon itself, and both events happen there. Which is why we justify that the muon sees the proper time because it's at the same position in this frame. Once you know who sees the proper time, then you know who sees the dilated time, which is the Earth, and you can perform the relevant calculation. Same thing for length contraction. We justify that the proper length is in the Earth's frame. Okay, this might not be very clear because basically the point at which the muon burst originated, so the muon burst origin and the oops and, and the Earth's surface, these are so like imagine there's a ruler here reading the length between these two points. Now, in the Earth's frame, these two ends are stationary. Whereas, like the Earth sees the muon moving down, right? If you go into the muon's frame, then obviously these 2 points will be moving up instead. Then this ruler is no longer stationary per se. So here in will the Earth's frame will measure the proper length because the two ends of this ruler are stationary. Whereas in the muon's frame, the two ends of this ruler are not stationary, they're moving up. So that's how we tell the proper length in this case. And again, once you have the proper length, uh you have the contracted length. So yeah, that's kind of the essence of this example. If you identify the correct proper quantities, you should be able to get this. So uh yeah, do read through this again if you're still unsure like how to tell proper quantities lah. Okay, moving on, there's this part about loss of simultaneity. Again, there's another thought experiment here which I will skip. The main point about this is if you have two events that are simultaneous in one frame, they will no longer be simultaneous in another frame, moving at some speed with respect to it. And if you look at this example here, it shows you because the light hitting the ends of the train are simultaneous in this frame, and hence they will not be simultaneous in the other frame. So this means that if you do relativity, simultaneity is lost. That's what we call, yeah, simultaneity is lost in SR. So you need to be careful when you use the word simultaneous because you need to specify which frame, basically, as different frames will perceive different simultaneous events. That's the crux of this. I don't think this is going to be that important. Yeah. Okay. So what we have gone through so far, like the basic effects, what we'll go through now is some mathematical tools to help you with SR lah. So of course, we'll go into kinematics first, then we'll talk about dynamics later. The first thing is the Lorentz transformations. This is what we call the LT for short. Basically, this is the way I like to think about this is just a mathematical operator. So I wouldn't think of the LT as anything other than a mathematical operator that takes in some space-time coordinates in one frame and outputs some other space-time coordinates in another frame. So, okay, this is the LT. Okay, so there are some things here there's some like definitions here that I will clear up first. This is what we call frame S. This is what we call frame S prime. And yeah, basically think of the LT as nothing more than an operator that transforms space-time coordinates in frame S to space-time coordinates in frame S prime. It does nothing more than that, and it is basically a purely mathematical tool lah, in this aspect. So the first thing that you might notice from here is we write CT and CT prime, right? Now this doesn't really break anything because we're just making our life more convenient that we're all dealing with distances instead of having one time. And actually most of the time, if you do like actually in some places you might even see the C ignored, written as C equals to one. That's also perfectly fine if you know what you're doing. There's a section on it later to kind of like I guess a disclaimer. But okay, we'll talk about that later. The more important thing is what is this transformation, right? So there are two main ways which you can express this transformation. First one is via equations, like that, which I don't really use this. Okay. Instead, I tend to use this because I think it's easier to remember this. So, but ultimately it's up to you, lah, like whether you're more comfortable with dealing with matrices or just equations like that. But I think this is quite nice to remember. You can see here that this matrix here is quite symmetrical also. So it should be quite easy to remember this. So yeah, you can see here, this takes in x prime ct prime. No, sorry, takes in x and ct and outputs x prime and ct prime. So it is really just an operator, nothing more than that. And with any normal operator, you also have an inverse operator or function. And yeah, in matrix form, it's like that. Now, why is matrix form good? Because I think it's quite easy to see that if you do something like that, if you apply the inverse LT to the normal LT, then you do some matrix multiplication. Yeah, there's a XCT here. Okay. Then you do some matrix multiplication. We get this. Uh, and uh, yeah, you get this. So what you're doing here is this is just the normal LT. This is the inverse LT, right? So if you physically think about it, you apply the normal LT first, then you apply the inverse LT afterwards. What will you get? You expect to get, of course, you expect to get the original thing because you apply a function, then you apply the inverse, you get back the original thing. And mathematically, it checks out loud. You can see that okay, this cancels out. Then uh okay, you can work out that this is 1001 XCT, which is XCT itself. So mathematically, this checks out the so you can kind of verify that the LT works, yeah, by doing this. That's also the advantage of the matrix formula. It's easier to do this rather than work out the equations using the equation form. Okay, so this is just a mathematical thing. Then uh okay. Okay, so there's a small disclaimer here. Direction is important because here we're assuming the standard configuration holds. This means that S prime travels with velocity v in the positive x direction relative to S. Positive is important because in some cases you might encounter S prime traveling this way with respect to S. In this case, then your beta is less than zero, and you have to put it into this equation. So the signs are important, but if you don't account for the sign, then you get something wrong. So it's quite important to see what direction your S prime is going with respect to S. before you apply the LT. Okay. You can also verify for yourself that if you have any two coordinates, let's say you have x1 ct1, x2 ct2, then you can verify that if delta x equals to x2 minus x1, delta t equals to t2 minus t1, you can verify that the LT also works for delta x and delta t. So the LT also works for space-time intervals, not just coordinates. Okay, so all this has been a lot of math up to now. It's just how to apply this function, basically. Now is okay, now there's going to be more physics where we consider relativistic velocity addition. So there's again a setup here, but this setup is quite important, so I'll go through it. So basically what's happening here is that you are on the ground here. You see a rocket moving. Okay, you see a rocket moving at V, and you see a GIF being shot at the rocket at UX. These two quantities are in your frame. So this is what you see as a ground observer. Now you're interested to find out what is the speed of the GIF as seen by the rocket. So here the rocket is stationary, and you are moving at V to the left based on what the rocket sees. So you want to find what is this quantity, right? So a very naive way to do it in classical mechanics, right? The naive way to do it is to literally add speeds like linearly. So if you add speeds linearly, you just get this. But because here the question says assume all speeds are relativistic, then there's definitely something wrong with this because what if let's say you put in some arbitrary values, right? What if v equals to 0.8 c? What if u what if ux prime also equals to 0.8 c? Then you get ux equals to 1.6 c, which is above c. So clearly something is wrong here. And the something that's wrong here is down to this equation because you cannot be seeing something travel faster than the speed of light in your frame. This is a physical object, and you definitely cannot be seeing a physical object traveling faster than the speed of light. So this equation is actually wrong in a relativistic scenario. And what I'm doing here is to prove to you how to add speeds in a relativistic scenario. So basically, the derivation here is again not very important. The important part is this. You should know this result by heart. It's called relativistic velocity addition formula. And yeah, this expression is super, super important. So basically, yeah, this is how you should be adding speeds in relativity if your speeds are quite high. Uh, Again, applying this is kind of just a matter of plugging in the numbers and making sure that you have the right speeds. So you need to know what the speeds are referring to because you're dealing with three speeds here. You're dealing with ux prime, and v. This is this is the speed of object in S, speed of object in S prime, and speed of S prime with respect to S. So there are three different speeds here. You need to know what you're referring to to apply this formula correctly. And okay, yeah, it's important to do a sanity check. So if your ux and v are in the same direction, please make sure that you obtain ux prime is less than ux. Otherwise, your signs are wrong. So yeah, please do a sanity check after using this formula. Okay, so that's for the x direction because everything here happened in the x direction. We assume this is the x direction now. But something interesting also happens in the y and z directions, quite interestingly. So again, again, just I think just memorize this. Yeah, it's fine. So these two are how you transform velocities in the in the y and z directions for movement in the x direction. So even though this is true, but this is not true. So it can be a bit trippy at first. The reason why it's trippy is because time is transformed, even though the coordinates are not transformed. So again, it's a matter of just applying these equations. And I think example 1.2 shows this quite well because, yeah, it kind of shows you how you apply the transformation for the y direction. Uh, this example should be quite straightforward. So just read it on your own. Make sure you know what speeds you're referring to and put in the correct speeds for the correct variables. Yeah, I think most SPhO questions, if they test this, will be somewhat like that. Just making sure you put the correct quantities in and you should get the correct answer. Okay. Uh, okay, I'll stop here for a bit. If there are any questions, do let me know. Okay. Let me check WhatsApp as well. Okay, got. Okay, can. There are no questions, so I will go on. Okay, there's one very long example here from Morin. This one is super, super important to understand. Once you understand this, you have understood everything that has been covered thus far. And okay, I will spend a bit of time on this to make sure you guys understand. So the scenario is there are two trains A and B, each have proper length L, move in the same direction, and they have these speeds with respect to C. And the first task is to find how long the how long A takes to overtake B with respect to C spring. And this one can be done using length contraction. So I think there are a few values of gamma that you guys should just memorize also. So 4 over 5 C is just 5 over 3. This is 3 over 5 C is 5 over 4. And basically C will see the lengths of these contract. This will contract to 3 over 5L. This will contract to 4 over 5L. And these two are moving. So the overtaking will last when the so it defines here the front of A passes the back of B is the first event, then the back of A passes the front of B is the second event. So the relative speed of these two with respect to C is actually C over 5. And this can be a bit trippy because you might be questioning where's the relativistic velocity addition? But the truth is, because these two speeds are viewed relative to C, the same observer, you're allowed to just manipulate speeds like that. So you don't need to do that because both are measured with respect to C. So you only need to do relativistic velocity addition if you have speeds that are measured with respect to different observers. So in the case above, you have speeds measured with respect to the rocket and with respect to you. That's why you need to do all these kinds of stuff. But in this case, everything is measured with respect to observer C. That's why you don't need to do this. And you can just take this simple difference. So this is probably the hard part to understand. After that, it's just a matter of simple kinematics. Yeah. Okay. So that's what C sees. And then you can also work out the same on what A sees and what B sees. So for what A sees, you need to use relativistic velocity addition for you to find what B speed with respect to A is. And then you do the same thing. You find the contracted lengths, you find the time using your simple kinematics formulas, and you get this. And you can do something similar for B's frame, or you can just conclude by symmetry. So yeah, I think the key point of the first part is just when do you apply relativistic velocity addition and when do you not? Once you understand that, I think it should be quite understandable. Then the next part is uh okay, the next part is you have a person D now, works at a constant speed from the back of B to the front. here, and he coincides with both events E1 and E2 in position. So now this should send alarm bells ringing, right? Same position of E1 and E2. What does this mean? D sees the proper time, which is by definition. But nonetheless, we can work this out because the two events are separated by a distance of L in B's frame and a time interval of this in B's frame. So we can find the required speed of D in B's frame for the two events to be at the same position, which is this. And then we can make use of the proper time thing to find what is the proper time from a dilated time. So TB is dilated. So this is kind of working backwards now using your time dilation. Yeah. Okay, there's some question in chat. Why it's proper time? Okay, because okay, it's kind of a text war here, but D walks at a constant speed from the back of B to the front and coincides with events E1 and E2 in position. So if events E1 and E2 are the same position, this means that it's proper time. This is just by definition. Yeah, you can take some time to understand the text more. Okay, okay. Can. That's good. Okay. Then yeah, all this is a matter of simple kinematics again. Okay, the last part of this question, you use the invariant interval to check. This is very important. So I don't think any SPhO question will explicitly ask you to work out the invariant interval, but in SPhO, please make sure you work this out. Please make sure you work this out to check in SPhO when you do the SR problem or SR problems. Because if you find out your invariant interval is different in different frames, then you definitely know that you screwed up somewhere. So that's a good sign to go back and check, rather than being unsure whether you are right or wrong. So yeah, please always work this out. Okay. Okay, so we'll move on to causality. This is basically saying that information is bounded by the speed c, and hence some events cannot cause others because they are separated by distances that are too far away, that even information cannot travel fast enough to reach them. So there's this word called causally connected. This is used to describe two events, E1 and E2. If E1 and E2 are causally connected, that means that one could be the cause of another. This also means that this also means that the order they are in must happen in the same order in all inertial frames. This means that if E1 happens before E2 in some frame, if they are causally connected, then E1 must happen before E2 in all other frames. Otherwise, physics will break itself. So there's this ratio here that provides some sort of necessary condition, but it is not a sufficient condition for you to conclude two events are causally connected. So you need to be very careful about this. If a question asks you to, uh, okay, so basically it just says that a question cannot ask you to prove whether two events are causally connected. This would never happen. But it could ask you to show A and B might be causally connected. This could happen. Or it could ask you to show A and B are not causally connected. This could happen. And if you have these two cases, just make use of this ratio. If the ratio is less than or equal to C, they might be causally connected. If the ratio is greater than C, then they're confirmed not causally connected. So this can only be used to disprove, cannot be used to prove. So be careful about this. Okay, but this is quite a small part. So yeah. Okay, the next one is relativistic Doppler. This one, there's also a derivation here, but in all honesty, you can skip this. Just focus on the main result again. And I think in the previous chapter, you should have learned about normal Doppler. Here, we take it a step further. We extend it to speeds that are close to light. And here, the same logic still applies when you deal with normal Doppler and relativistic Doppler. If you're, so suppose you have this source here, and you have an observer. If your observer is moving away from the source, then f prime must be less than f. Now, you can check here that if you plug in any positive value on beta, your f prime is indeed less than f. So this applies. Instead, if your source is, okay, if your observer is moving towards the source, then f prime must be greater than f. And instead, you should be writing this. So again, the sign here is very dependent. So the sign here is very dependent on the physical situation. You need to assess whether it is a case of must the perceived frequency be greater or smaller than the emitted frequency. And you need to check this logically lah, to figure out what's the sign that you should use. Yeah. So make sure to check logically so you don't flip the signs. And this one is what we call the longitudinal Doppler effect. There's also another thing called the transverse Doppler effect, but this is not important. This is outside of the syllabus. You can read more if interested. And what we assume to be the case usually is that problems are referring to the longitudinal Doppler effect if it's not stated. Yeah. It's also just a matter of applying this formula again and applying it with the correct signs of beta. The next concept is on proper acceleration. This one is a bit tricky, but it's also really mathematically involved. So the point of this is uh okay, the point of this is actually just this. So again, through the notes, you can see many derivations of things, but they are really, really not essential for SO. Like you just need to know the final results and you should do fine. So what is important about this thing? It just means that acceleration, your proper acceleration, which is A naught, and your lap frame acceleration, in a case where your acceleration is parallel to your particle's velocity, is related by 1 over gamma cube. Now, this has quite important consequences, as you will see in the problem later on. I think it's one of the SPhO problems where you try to solve for velocity as a function of time, and then try to solve for x as a function of time. You can even try to solve for the lap time as a function of the spaceship time, etc., etc. And this actually reduces to a differential equation that you need to integrate to solve. So yeah, actually just getting this after you get this, you still need to do a bit of integration now to solve for these relations. This is one of the problems later on. So I will not go into this for now. There's also this perpendicular case, but it's really not as important. Okay. So there's this whole section here on Minkowski diagrams. I will not go through this in detail. Actually, I will not go through this for this lesson because uh this is just an additional thing. If it helps you, then it helps you. But if it doesn't help you, then you are free to skip this. But it's a more graphical way of representing space-time coordinates and how they transform between frames. Uh, I think what I've written here should be quite self-sufficient, so you can just read through that on your own. But other than that, I think we can move on to relativistic dynamics but I'll just stop for a bit for any questions on kinematics first. Yeah, I'll also check WhatsApp. Okay, there seems to be nothing. Okay, there seems to be nothing. So, uh, yeah, that's all for kinematics. The more important concepts is uh LT, proper length time identification. uh, I would say relativistic Doppler. These are the more important concepts now. Please make sure you know this for SPhO at least. Okay, then we'll move on to dynamics. Dynamics might actually be simpler, like depends on how you look at it. But anyway, the first thing I will talk about is this thing called relativistic mass, which actually there's a question mark here for a good reason because I don't encourage the use of this. I'm just going through this in case SPhO shows you the term relativistic mass and they expect you to know what it means. So this is what it means. Uh, M equals gamma M naught. M naught is what we call the rest mass, and the rest mass is the mass of the object in its rest frame. Yeah, simple as that. So basically, this thing claims that if you see any other frame where the object is moving, then the mass of the object actually increases. That I saw one question. Oh, uh, wait. I'm wait. Could you send could you send me the question? Because I don't think I have any question in my notes using density and that. Yeah, thanks. Okay, thanks. Okay. Anyway, yeah, there's this thing where they claim that the mass of a moving object increases. Now, this was made for convenience. You see in later equations why, because you will see this combination of terms appear quite frequently. But I really don't encourage using this because it gets really confusing and yeah, it's really not. There's really no caveat. Okay, there's no advantage in using this with compared to like any other normal formulas. So just think of everything as a rest mass. It's much simpler that way. And then just think of how other quantities change and not how the mass change. Yeah. Okay, so here, okay, so here there's this thing here. This is about energy. So okay, on first look, you see this term appear, right? Gamma m. Okay, it should be an m naught here. So I guess you could write this as mc square if m is your relativistic mass. But you can see how it gets confusing because you don't know what, because your m here might be confused with the rest mass. And then it just makes no sense because you're just dropping gamma out of nowhere. That's why we don't recommend using relativistic mass. Yeah. But anyway, back to this. Uh, this one is super famous. It's just the Einstein's mass energy equivalence. And basically, your kinetic energy is given by this term at relativistic speeds. And your total energy is the sum of kinetic energy and rest energy, which is given by this. Okay, so there are three formulas here, which might seem completely out of nowhere, and you'll be right to question that. So, where do these come from? These actually come from empirical results, which is why you don't see any derivation for these formulas. And they're just there because that's what like early physicists found experimentally. Yeah, but they are correct. Just remember them and remember how to apply them. Remember the differences between them as well, because kinetic and I think kinetic and total are quite commonly messed up. Need to remember this is gamma minus one and this is gamma. Yeah. So these formulas are just formulas. Just just know them. Again, relativistic momentum is also defined like that. This is also quite empirical, so there's no way for me to derive this. Just know how it's defined and how to calculate it. Okay, so there's also this very neat equation here. It's called the relativistic dispersion equation. This combines a lot of terms. You have total energy, you have rest mass, you have momentum, all combined into one equation. And this is a very neat equation because most of the times when you're converting between total energy and momentum, you will need this equation. It makes your life much simpler. Okay, so these are all just definitions of quantities so far. This is also another reminder that energy and momentum work just like in classical mechanics. You have COE and COM, they still exist, but you need to choose the correct relativistic expressions to do these laws. And which means that you need to, if you do COM, you need to use relativistic momentum, for instance. If you do COE, you need to use the relativistic energy. So make sure you use the relativistic variance of the expressions. That's just the bonding here. Uh, okay, you might remember this from classical mechanics. These still hold in special relativity, thankfully, and these might be actually quite useful because you want to work with energy and momentum most of the time when you're dealing with dynamics, instead of actually force and acceleration. You'll see later on in four vectors why this is the case. But anyway, there are a few examples here. It's just applying the energy and momentum formulas. So this example 1.4 is quite straightforward. You can just be on your own. It's basically just applying all the formulas that we have went through above to get some results. Example 1.5 is slightly more involved, but if you work out your vectors properly, you should be able to form your correct differential equations to solve the ODEs. Uh, this one, okay, I will also not go through this in detail because the main part is just remembering gamma exists. The rest of it is literally what you work out in a normal uh dynamics problem, except with the different definition of P. So yeah, you need to use this instead. And then you differentiate both with respect to time. Okay. Yeah. So that's the only difference. Other than that, all your forces, everything are the same. So yeah, there's not much to talk about for this example, if you're careful with your ODs. Okay. So these formulas alone kind of make up all of relativistic dynamics that you need to know, which is quite nice because there's not a lot of stuff that was covered. It's just a few formulas for energy and momentum. But the truth is, most of the time, if you just work with these formulas alone, they're not the best way to solve problems. That's why I'll be introducing this trick called four vectors in the idea section later on, which will help to solve a lot of it will help to solve a lot of dynamics and collision problems in relativity. Okay, are there any questions about relativistic dynamics at this point? Yeah, yeah, waiting. Ignore the but okay, okay, this is just a matter of preference. I think most this is just like a made up concept basically to make stuff easier to explain because the combination of terms gamma and m naught appears quite a lot in the other expressions, which is why they made up this term to explain it. But it's better to just ignore this concept and treat everything as a rest mass. So it's in a way it's easier to think mass is invariant, but other quantities like momentum and energy change, rather than say mass changes while other quantities don't. Yeah, yeah, yeah. Okay, great. Okay, then we'll move on to ideas. So the first idea is about light time. Okay, there's no example here, but I will go through one of the problems later that needs this. Basically, this is just saying light needs time to travel. Don't miss that out. And there's this sort of like English difference between observing and seeing. When a question says observe, it means when the event actually happens. But if the question says see, then you need to account for the time taken by light to travel to your eyes. That's just the main difference between these two words. So you need to be very careful with the question phrasing. They might try to throw you with this, and if they do, please make sure you account for the time light takes to travel. So that's just light time. Uh, Rapidity is quite mathematical. You can see here that you can see how it's defined here. And what it does is basically it makes your relativistic velocity addition simpler to do because rapidities are linearly additive, meaning you can do this. You can add up. It's perfectly legal to add this up, but it's not legal to add this up for speeds. So that's why it's more convenient to do this. The convenience really shines when you have to do many relativistic velocity additions in succession, which you will see in example 1.6 here. You see you have frame S1 at beta with respect to frame S, S2 at beta with respect to frame S1, and you do this all the way until frame S10. So if you didn't know anything about rapidity, you'll be forcing yourself to do 10 relativistic velocity additions, which is quite insane, and no one wants to do that. But with rapidity, you can just say the final rapidity is just 10 times the rapidity of each, which is just 10 hyperbolic tangent inverse of beta, as you can see here. And so the desired velocity is this. So isn't this much neater than doing the process 10 times? So if you actually did the process 10 times, you get a huge expression, which turns out to be equivalent to this nice little expression here, if you know some hyperbolic trigonometric identities. But anyway, you can reduce it to this form, and you can reduce it to this form. You can check the limit if beta is much less than 1. This will reduce to this will reduce to 10 beta c, as what you expect under Galilean relativity. So I think rapidity is more important if you face any problem that's quite contrived. So if you face any problem that requires you to do many relativistic velocity additions, then this will become your best friend. But I think these kinds of problems are usually quite contrived. So yeah, you might not see them as frequently, but if you do, then this is a good trick to know. Okay, so again, it's all just math lah. So yeah, not much physical insight into this. Okay, now we come to the part I was talking about, which is four vectors. So what are four vectors? There are a set of four quantities, obviously, and the key thing is they transform the same manner as CT, XYZ under the LT. Okay, so this is very important. So this literally defines four vectors and what differentiates them from any four random quantities. So you know that CT, XYZ transform like this under the LT. Okay, so if you draw an analogy to any four vector, let's say this is a four vector, right? Then what can you say? Well, you can say this. Okay, V1, V naught prime. Yeah, this is literally just matching V naught to CT and V1 to X. Yeah, which gives you a very powerful relation that you can use between quantities in a set of between quantities in a four vector. So actually just doing this alone, you can derive many powerful transformations, even for quantities that are not just X, Y, Z, T. Okay, so what do I mean here? So yeah, this is by definition. We assume V2 and V3 are not transformed as per the standard configuration, and this is what defines a four vector. We have this thing also called the inner product of two four vectors. Basically, this is dot product but for four vectors now. So, but there's a very special thing here. This negative sign for the zeroth component. The rest are all positive, so that's fine. But there's a negative sign here. Please remember this negative sign. If you do not remember this negative sign, then everything here will fail. Basically, this is not exactly the dot product, but it's a dot product with the first component negated. Okay. I see a question. What is the point of this? Okay. I will come to this shortly. I mean, right now it seems kind of abstract and mathematical, but this four vectors is actually quite powerful for special relativity. Okay, uh, so yeah, some notation differences. These two mean the same thing. Okay, uh, yeah, this is quite mathematical. If you want, you can read about what a metric signature is, but I won't go through that. Okay, so why is inner product important, right? The elegant thing about the inner product is that the inner product of two four vectors is invariant across all inertial frames. This means that if you have v dot w is equals to v prime dot w prime for all frames S prime, it is invariant. And because of this invariance, usually this means you can pick a convenient frame to evaluate this inner product in. And then once you pick that frame, you move to the frame that you want to do your calculations in, and it'll stay the same, which makes it very elegant. Okay, I think, okay, it might seem a bit abstract, but again, there's an example later to show you about this invariance. Okay, so far we talked a lot about four vectors and their properties, right? But what exactly are four vectors? What are examples of four vectors? Clearly, well, the first one is the four position, because we've mentioned that how four vectors are defined are using this, they must obey the same LT as this. So obviously, this is a four vector. So how do we get other four vectors from this? Now, because four vectors, if you multiply or divide any four vector by another Lorentz invariant quantity, you get something that's also Lorentz invariant. And this other thing that's also Lorentz invariant is going to be a new four vector, because if you take the inner product of it with anything with another four vector, it will still remain Lorentz invariant, because a lot of things when you deal with four vectors, there's this Lorentz invariance now. Okay, so you see here that there's a hint to consider proper time. How? So we can do something like that. This quantity will still be Lorentz invariant because both are Lorentz invariant. And then we need to remember how proper time is defined. Okay, so you will get this, uh, which means that you can differentiate component-wise with respect to time, and you will end up with this expression. And this is what we call the fall velocity, which I guess is the time derivative of the fall position. And this thing is also a four vector. Okay, so cool. We have got another four vector. We can take this up one step further. We can get another four vector, and you guessed it, we are going to get the four acceleration. So you can do a component-wise differentiation. Then, okay, this is a bit tedious, but you can see I skipped it here also. You eventually end up getting this for your four acceleration. So you see, just like that, you have gotten two more four vectors that also satisfy the LT with their first two components. So this is very cool. And like this, you can technically generate a lot of like, okay, you can technically generate like an infinite number of four vectors, but these are the more important ones that we use in physics. So we have found the four acceleration and four velocity. Okay, so I guess you can also look at equation 53, right? Like this is quite ugly. This also explains why we don't work with acceleration. We rather work with momentum and energy. Because no one wants to deal with gamma to the power of 4 and all these terms. Yeah. How did you get the Lorentz to the power of 4? Okay, this one need I think okay, just be a bit patient with the differentiation. I think yeah, make sure you product rule this and then you find this properly, then yeah, just be a bit patient with it. I can I can work through this after lesson if you need to. But I'll not focus on the math for now. Yeah. Yeah, yeah, it's okay. Okay. Uh okay, there are, so right now we know about the existence of three, four vectors. Let's look at this example. We want to find the square of the magnitude of the fall velocity. So this is just literally evaluating it. Okay. And boom, you realize you get a constant, which is invariant across all inertial frames. So this kind of verifies how, okay, this kind of verifies the statement above, right? The inner product of two four vectors is invariant across all inertial frames. And yeah, okay, what is the square of the, what is the square of the magnitude negative? Oh, because, okay, I mean, you shouldn't think about this in terms of real numbers of the way we, because of the way we define the inner product. The first term is negative. We put a negative on the first term. I guess another way of thinking about this is if you want to preserve the definition of the dot product, then you can kind of introduce I for the first term. So in some places you might see this. You might see them write it like that. Uh so in this case, if you follow this, then you get the negative sign out for the first term. But I don't prefer to write I because I think it's easier if we just don't introduce uh complex numbers into this. Yeah, so that's how I mean that's how I do it. Like you are free to do this if you prefer just working with complex numbers. Yeah, so it's still possible to have a negative because of this negative sign here. That's the reason behind it. So yeah, you see here the first term is negated while the other term is positive. Yeah, I hope that answers the question. Okay. Uh so yeah, you see, yeah, here it says it's a constant. Then yeah, so that's part one. For part two, this kind of shows you why the Lorentz invariance of these inner product is important. Because here is where we use the convenient frame trick. So we have two objects A and B, right? We want to find the inner product of their four velocities. Now, it's not stated which frame this is in because it's the same for all inertial frames. We want to find, we want to show that it's equal to this. So what is a good frame we can use for this? Well, a good frame we can use for this is a frame where as many of the components of the fall velocity are zero as possible, or as simple as possible. In this case, if you go into A's frame, then A is just stationary like that. B is moving at V rel with respect to A, because that's your relative velocity. Now, if A is just stationary like that, remember that the remember that it's given by this, and gamma is just equals to one. So, oh, okay, because it's stationary, and V is zero, so it's just given by this. This is the fall velocity of A. And three components here are zero. So it becomes very simple, right? And you can write the fall velocity of B like that. And then you can do the inner product. You will get this. as required. Yeah. So this shows you like so the best frame you can go into here is either A's frame or B's frame. It's symmetrical in B's frame. So yeah, don't worry about that. So so how to choose a good frame? Make make the math simple for yourself. Okay. Wouldn't gamma rel and B rel change based on the frame they are measured in? Uh Gamma rel and V rel. So no, V rel is defined as the relative velocity between A and B. So you need to be either in A's frame or B's frame for this quantity to even make sense. And gamma rel depends on V rel. So yeah. Okay, yeah, I'll stop here for a bit. Okay, why is the dot product negative? Wait, you mean this one? Yeah, because the first because if you multiply these two, it has to be negative. That's what the rule says for the first term. Then so on is all positive lah. Yeah. So that's why negative. Okay, there's another question. Isn't that value supposed to be invariant? This value? Yeah, this value is invariant because VREL is defined between A and B, right? Which means that you go into either A or B's frame to find it. So so in a way it's so yeah, in a way it's not it will be invariant because this value kind of only exists in here. Or is that not what you mean? I'm a bit confused. In a previous question, do you have a relative speed between A and B measured in C's frame? Uh, wait, where is this? Hmm. Oh, example one. Okay. Where is it? Oh, it's here. Okay. Uh, relative speed between A and B measured in C's frame. Yeah, that's CO5. Then, uh, okay, CO5. Oh, wait. Okay. Do you mean, wait, okay. So I'm going to use this example as an example. So VREL is CO5 in C's frame, but VREL is, what's that? 5C or what? Is this what you mean? Oh, okay. Wait, that's a good question. Let me think. Uh, okay, I think it's just uh I'm inclined to believe that this is just a problem with how yeah, I think it's just a problem with this example. Okay, I mean the wording was copied from the source, but here it says that VRAL is their relative velocity. It didn't say with measured in what frame. And the implicit assumption is that it's measured in either A or B's frame. So that should be part of the resolution to this. But is it cause when you go into another random frame then A four velocity? Yeah, yeah, it's different also. So okay, I guess you can work it out and see. But yeah, the VA is also different, so it also changed stuff. But I guess part of the confusion is also the question itself. Okay, I will edit this stuff. Yeah, don't worry about it. Okay, I hope the confusion is sort of cleared up. Okay, I'll return to the meeting chat later because I think we're running a bit short on time. I'll go through this part about form momentum first. So, uh, form momentum is defined like that, and okay, since it's defined like that, it's a four vector, right? So you can also write this. This is valid because it's a four vector. So that's cool. Like this thing is kind of non-trivial, right? But because you have this thing as a four vector, you have this relationship. It's true. So that's a cool thing. And yeah, that's a way to transform energy and momentum between different frames. Okay. So what's the point of knowing all these four vectors though? The most important one is probably going to be a four momentum when you talk about relativistic collisions. And it all boils down to conserving four momentum whenever you have a relativistic collision. So what happens when you conserve four momentum? You just have this whole thing equals to other four momentum terms added together. And this, if you think about it, boils down to having one COE equation with all the E terms, and then one COM equation with all the P terms. So that's essentially what this thing is about. And there's a small framework here on how you can apply CO4M, I would call it. And yeah, that's sort of what you should be doing for every relative state collision question. Okay, the sort of non-intuitive part will be this: square both sides of the equation. Okay, why are we squaring both sides of the equation? Because the inner product of any four momentum with itself will give this, which you can prove using the dispersion relation. So if you are not convinced, I think you can try it for yourself. Try to inner product this with itself. See whether you get this. And if you do get this, this is it. I mean, clearly this is invariant, right? And because it is invariant, then it's quite nice because yeah, it's a quite simple term and it's easier to work with this than having unknown energies or momentums in your expressions. Okay, so this example is very critical. It's basically how you solve any problem of this type. Okay, first of all, you always want to write down your four momenta. So in this case, you have you have two particles and you have a new particle. So you have three four momentum terms to write down. So let's call this P1 mu. and we can write it like, okay, so we have this, right? Then recall that E equals to gamma MC square, P equals to gamma MB. So this would just be E over C is gamma MC. This would be gamma MV. This would be 0, 0, where we assume that this is the x direction. And for particle 2, you write your form momentum, it will be gamma MC squared, so half gamma. Oh wait, oh the gamma's the same. Okay, that's cool. Okay, uh, gamma MV, so but in the negative direction. And then this one you have P3 mu, but you kind of don't know anything about this now. I'll just what is the new mass? Okay, M1. Okay. So whenever you have a problem like this, start by writing down your four momentum terms like that, and it'll make stuff much simpler to do. Okay, once you have these terms, right, clearly P1 mu plus P2 mu equals to P3 mu. That's how CO4M works. Okay, and the next step is after you have this equation, you want to square both sides of the equation. So what happens if you square both sides? Then P3 mu dot P3 mu will just be very simply this. That's the right hand side. Whereas for the left hand side, you sort of get, okay, I'll just, okay, I will not skip steps for better understanding. So, okay, P3 mu, P3 mu, okay, I'm just going to write it like that. P1 mu, P1 mu plus P2 mu, P2 mu plus 2 P1 mu, P2 mu, okay, which gives this, this will be minus m squared, c squared. For 2, it will be minus m over 2 squared, c squared. And then you have plus 2 P1 mu dot P2 mu. Okay, so this is where you need to be careful with signs. We take the first term times the first term times a negative sign. So that will be negative half gamma square m square C4 plus the second term times the second term without a negative sign. But okay, there's a negative there already, so that will just remain negative. So that'll be half uh gamma square m square b square. Wait, oh wait, no. I oops, okay. Yeah, this should be it. Yes, okay. Then the rest of the terms are zero, so we just ignore them. Then it's just a matter of rearranging this for now. And I think I do that here. Yeah. So okay, there's this huge mess here. This is the exact same thing as the last equation which I wrote. So yeah, this is just this. Okay, but uh, like other than this is just all algebra. So I think the main point of this kind of problems is how you even get to this equation, right? So how you get to this equation is you need to start by writing your form momentum correctly for all particles in all states. Once you have these three terms correctly, you want to square both sides and then get some, and then start by start by using this. So start by using this after you square both sides. And then you can simplify a lot of stuff. And it's just a matter of rearranging. That's just the general way of doing it. But in some cases, it might be a bit ambiguous because, okay, you see this later in the problems. It might be a bit ambiguous on how you should rearrange the equation. So that's where this step two comes in. You want to identify the known and unknown four momenta and isolate an unknown to one side of the equation. So why is this useful? Because if you isolate an unknown to one side, let's say you isolate, okay, let's say you have four terms, right? Let's say you have something like this. Let's say you don't know what this is, and you don't care what this is. And if you do this, if you square both sides, then you can very simply throw away this and make it into a minus m4 square c square term, which is very convenient for you because you really don't care what P4 is at all. And you're just doing something in terms of M4, which I guess you should know. Yeah. This kind of comes into play when we talk about this thing called quantum scattering. If you want to derive it, uh, yeah, quantum scattering. I think it's also, yeah, it's in the problem status, so we'll look at it later, lah. Yeah. Okay. Okay. That sums it for relativistic collisions. There's a small disclaimer here. If you want to set C equals to 1, please make sure you know what you're doing because if you do that, you cannot do dimensional analysis. Uh, as a general rule of thumb, you shouldn't be using C equals to 1 for SPhO problems because I don't think they will be that complicated and you wouldn't need to write that many factors of C. So I'll just recommend not doing this. Okay. Uh, any questions about form momentum and relativistic collisions? Let me open WhatsApp as well. Okay. Uh, doesn't seem like it. In that case, we'll just go straight to the problems. Okay. I'll go to the few requests first. Okay. This one was requested. Okay, so uh this is quite hard, so I don't think it'll be in SPhO. But anyway, uh basically the situation is here. You have a ship of mass M, you have light from lasers on Earth, you have total power P, then you want to find how the ship accelerates basically, based on the light reflection. Okay. So qualitatively, if you want to understand this, it should be quite simple because you're just looking at momentum transfer from photons, which gives a force to the ship and then gives an acceleration to the ship. Okay, so this should be quite simple to understand how the problem works. But quantifying this is not as easy because uh when you deal with normal reflection, right? So uh so when you deal with normal reflection, suppose you have light coming and then you have some object moving at v. But suppose your v is very, very small, such that it is non-relativistic. And then say your light bounces back and say that this is perfectly reflective. When you deal with this, yes, the situation is very symmetric because your light bounces back like that, and then the momentum transfer is just very simple, right? This is what you claim for a non-relativistic scenario. Now, but what's the issue with this for this problem? The issue with this for this problem is that your thing, which is your ship here, is moving at a relativistic speed. So when your source emits photons, you need to consider the longitudinal Doppler effect because uh this thing is relativistic. So you cannot just say that it's symmetric like that. So how does this matter? Okay, because let's say your source produces frequency f then when you reach the ship is kind of the observer, right? So the observer will instead perceive a new frequency. Because the observer is moving away from the source, it will perceive this. This is perceived by the observer on the ship. Then when it comes back to Earth, so when it comes back to Earth, right, you can imagine the roles of the observer and source being swapped around. So when it comes back to Earth, ship is now the source, Earth is now the observer. But then but from the frame of the ship, your Earth is moving like that as you send back photons at F prime, which means that there is another Doppler effect here, called this F double prime. And since it's also moving away, it will be reduced. And your frequency as perceived by the Earth is this. So if you combine that, that will give you this. So what's the significance of this? This means that as viewed by Earth, the incoming photon will have, okay, F equals to F, but the outcoming photon going back will have, will have F. The outcoming one will have F, 1 minus beta, 1 plus beta, which is not symmetrical. And I think this was the key issue with the argument that was presented. Yeah. So the relativistic Doppler effect matters here, and that causes the frequency to be different. And because it's different, you cannot uh simply consider a symmetrical case like that. Yeah, it doesn't really work. But the momentum transfer thing still holds. So you can still do, so suppose you have one photon, the momentum transferred by one photon will still be, okay, these two are in opposite directions. So it'll be this, one plus, okay, this two. Okay, why is there a double Doppler shift when viewed from Earth? Okay, because, okay, this is sort of like a normal reflection example lah. Like, uh, okay, the first Doppler shift should be quite obvious because the ship is the ship is the observer, the Earth is the source, the observer is moving away from the source when the ship receives it. So that's the first Doppler shift. The second Doppler shift occurs because the ship is reflecting back the photons to the Earth. When it reflects back, the ship is essentially acting as a source to send back photons, and the Earth essentially acts as an observer. But the ship is also moving, so the source is now moving away from the observer when it goes back. That's why there has to be a double shift. That's the reason for it. So I guess this part explains it. Yeah. Okay, the first shift is because the ship is receiving the original photon from the Earth as it moves. That's the first shift, as viewed by the ship. Yeah, it was reference to the ship, not Earth. Yeah, yeah. Then the second one is with reference to the Earth. That's why. Yeah. Yeah, so that's the reason for it. Okay. Uh yeah, anyway, back to this part. Okay, so this is the momentum transfer per photon, but this is only for one photon, remember. Uh okay, now there are a few subtle things that you need to think about. So you know that F equals to dp dt still holds, right? And we have the power of the laser. Okay, I think this is going back. Okay, the notation is going to get quite confusing. So I'm gonna denote power with a dash below it. So you know that's P for power, not for momentum. Power is defined like that. And if you have n photons, it will be defined like that. So dn dt is the rate at which photons are emitted from the laser. Oops. This is the rate where photons are emitted. But the thing is that the rate at which photons are emitted, unfortunately, isn't the same as the rate at which photons are received because the ship is moving with respect to the Earth. So the rates are going to be different intuitively. And they are related by this. I guess to make notation clearer, NEM is emitted. So they're related by this. Okay, I'm gonna receiving. But this is just purely by like relative speed, right? Of like approach. I I hope you're able to see this because this is quite important. I think it's a point that many would miss out. If you're able to intuitively see this, then I think there should be no problem. You can't see it. Like, oh, you can't see this. Okay. Uh, okay. To explain this, sort of like, okay, you have C, right? Then you have V. So sort of think of C minus V as the relative speed. And basically, the rate of receiving, the rate of receiving must be smaller than the rate of emission because this thing is moving away. So it will only receive at a speed that's kind of scaled by a factor of this over C for, yeah. Okay, I think that should be good enough. Yeah. Yeah. Okay. Okay, so if you have established this, then uh receiving is this. Uh if you're concerned with F is gonna be uh EN receiving, EN REC DT times the momentum change per photon. So that'll be uh HF over C 2 plus 1 over beta. That'll be the force on the that's the force on the ship due to the rate of receiving of the photons. And uh so this would be 1 minus beta dn emission dt hf over c to 1 plus beta dm. Yeah, so then you can use this. This would be dn emission dt equals to power over hf. So power over hf, hf c to 1 plus beta. Hf cancels. Nice. Power. So this will be 2 power over c 1 minus beta 1 plus beta. Okay. So that's the first part. That's the force. Now, how do you form a differential equation from this? Now, if you go from this from another angle, you can do this. And essentially it will reduce to, okay, it's going to reduce to this. And you can really work it out. It's going to be a little bit tedious, but you can work it out. And yeah, these two are basically equivalent to each other. So once you set these two equivalent to each other, then you will get some differential equation in terms of uh you get some differential equation with V and T basically. Okay, there's another chat. Isn't there a also a force where the light is re-emitted at the second Doppler shift? Uh the force originates from the fact that it is re-emitted. But in this case, you're considering the total change in momentum of the photon between the state where it's emitted and between the state where it returns. And this must be the total change of momentum of the ship as well. Yeah, yeah, okay, it's fine. Uh, okay. Back to this. So yeah, you can sort of form an equation like that. It's gonna be quite messy to work out, but I think if you do everything correctly, you should get. Actually, what will you get? You get something like okay. Uh, if you work everything out correctly, you get something like this. Yeah, where where c equals to 1 here. I think this is just for, yeah, this is for convenience now. So, okay, this is not essential. Again, it's math. I always emphasize that the mathematical steps are not essential because I believe that everyone can do it. The essential part is everything here. The fact that you must first realize, okay, I'm gonna write it here. Must first realize two Doppler shifts, so not symmetric. Then how to relate F equals to dp dt in two ways to form to form ODEs, and the rate and the fact that the emission rate is not the same as the receiving rate. These are the three key points of this question that it should teach you. I think as long as you understand these three key points, you have understood the question. And that's honestly quite good enough for a last question of the problem set. Yeah. Yeah, I'll work this out like in detail in the solutions document, so don't worry about it. Can you explain too? Okay. Uh, okay, so what this means is there are two ways to do this. First one is definition, product rule, chain rule. Yeah. This is the definition way. This is equal to doing it, yeah, from the Doppler shift. Yeah. Basically just equating these two. Yeah, that's what it means. O- okay. Any questions about this question? I think this is really, really complicated. So nothing of this difficulty is going to come out in SPhO. So like please don't worry about it if like you're a bit lost or anything. Okay. If not, I'll move on to other questions. Uh this one was also requested. I think okay, this is definitely much more representative of SPhO. because it's from a past SPhO itself. Anyway, the point of this problem is, okay, you have two things here. This is moving at v. This one is stationary. You want to find uh the phase difference between these two. Okay, so what you can do is the speed of light in this trial. I'll call this VB. This is C over N. And I think this is quite normal because this trial is stationary. But the speed of light in this trial is different. So the thing is, in this trial's frame, I'll call this VT, for V top. VT prime equals to C over N. This only holds in the frame of the trial because in the frame of the trial is stationary. The light still moves at C, and so the speed of light will be C over N in the material itself. This happens in the trial's frame. But in the lab frame, trial moves at V to the right. Okay, this is to the right. So your V top in this lab frame will be V top prime plus V, 1 plus V top prime V over C square by the relative velocity addition. C over N plus V, 1 plus VT square. Okay, C over N V over C square. Okay. Okay, a whole bunch of simplification. Okay, so that's the speed of that's the speed of the light on the top at the top. Yeah, because of relativistic velocity addition. So because these two lights have different speed, that's where the phase difference comes from. So the phase difference in this case is just going to be okay, you have this relationship. All this is from waves. So yeah, to understand this, you need to know your waves well, lah. Okay, so this is time taken to travel in bottom or top. Then this will become yeah, this will become this. Actually, yeah, it's easier to just get here to here. Okay, it's fine. Uh, then you simply sub it in. Then you okay, and then when you simplify, you should be getting this when you simplify it. Yeah, that's the phase difference. So again, key point of this question is when you have the thing, when you have the whole medium moving, right? You need to add the speeds up in using relativistic velocity addition. The C over N thing only holds in the frame where your medium is stationary. If your medium is not stationary, then you need to speeds up, basically. And the phase difference arises from the difference in speeds. That's the crux of this question. Why does the question specify V? Actually, that's a good point. I'm not sure what the original S4 question put at. Actually, if anything, this shouldn't be there. Yeah. Okay. Please ignore this. That's just partly. Oh, is it so that? Oh, oh. Actually, Actually, yeah, I think it's because of that, but I think it'll be easier to just say don't account for length contraction. Yeah, because this might be a bit confusing. Okay. Okay. I guess as you can see, there's some imperfections in the earlier years. So yeah, it's quite normal lah, unfortunately. Okay. I think this problem should be fine. Yeah. Okay. There are more problems that I wanted to go through. Let me see which one okay, I think can go through both of them. Yeah, sure. Okay. So the first one is gonna tell you about light time. So the situation here is basically you have a bunch of students here. You have this guy here, the teacher zooming past at V, this is Earth, and you would like the class to have time T to complete the test. This will obviously be in the frame of the Earth. So the Earth frame must record a time of T. But because this teacher is moving away, when this teacher is somewhere here, needs to send back a light beam to Earth. And clearly there's some distance here. Let's say this is X. Okay. So there's some distance X here, which means the light has to travel this distance X, which means there's light time. So this is one of the scenarios where you need to account for light time. If you don't remember light time exists, then I think this question is meaningless now. Like it doesn't really make sense anymore. It would just be a simple time dilation question if there was no light time. So this is one of the scenarios where you need to account for it lah. And so how do you account for that? How do you account for it? So let's say that okay, let's say light pulse is sent out at uh okay, let's say light pulse sent out as sometime t emission at t emission with respect to Earth. So let's say this happens, then uh light time will be okay, this is the light time to go back to Earth. And within this, you need to identify that the proper time where events happen at the same position. In this case, the events are start test and end test happens on Earth because that's what it says here to complete the test. So this thing, so this thing happens on Earth, right? So uh, which means that the this guy, the the teacher is going to see the dilated time with a factor of this. That's the light time. So uh, you want the arrival of the thing to be exactly at time big T. So for the light pulse to arrive back at T, we have T emission plus VT emission. Let's see. equals to big T because you accounted for the lag time. And you can rearrange this a little bit. T emission is T over 1 plus beta. So that's the time which the light must be emitted. And at this instance, what does the clock on what does the clock on the teacher's when should she send out a beam of light, right? So this is the teacher's clock. So if this is the time of emission on the Earth's frame, then teacher in the teacher's frame, wait, sorry. Okay, wait, sorry. Ignore this part. Okay, because ignore this part. I'm kind of live solving this, so yeah, ignore this part. Basically, the thing here is that okay, the Earth sees the teacher moving, so the Earth will see the teacher's clock moving slow. I think okay, I might not have mentioned this earlier, but there's this thing called moving clocks run slow, and that's like a easy way to remember like which clock is running slow lah. So if the Earth sees the teacher moving, the teacher clock is running slow, right? With respect to the Earth clock. This means that the teacher time is actually uh it's called as this. There's no good notation. Uh divided by gamma. This means there's actually this. Because okay, so why one over gamma? Because teacher clock is moving, so it runs slow. That's how it works. Yeah. And that's probably an easy way to remember this, like where the gamma goes. Okay, so I guess if you work this out properly, you should get this. Okay, I hope this is correct. I don't have the answers with me, but uh if any of you are like working this out, so you can let me know if you got the same thing. But otherwise, okay. Otherwise, I don't think this question has much going on. It's just showing you like, okay, if you have light time, find some you need to find the time of emission of the light, which is gonna happen before like whatever time you're considering. And then once you find a time of emission, you need to work things out with normal kinematic stuff. Solve the crux of this problem. Yeah. There's nothing more that's quite insightful, I would say. But I'll check this out and update the solutions document once I get to making that. Okay. Uh we have 1 minute left. Okay. I I guess I can this is also quite important, so I'll just try to speed run this as fast as I can. But anyway, this is what I was talking about earlier. This is quantum scattering. You have a photon here, it scatters off a stationary electron and it goes off again. So what's the point of this problem? This problem asks you to consider momentum conservation and then energy conservation, right? But there's an easier way to do this because you know about four momentum, which means that, okay, so let's say this is P1, P2, P3, and okay, no, let's call this P3 and P4, where P1 is the incoming photon, P2 is the stationary electron, P3 is the uh, outgoing photon, P4 is the outgoing electron, Then if you have four momentum, it's just a matter of writing this. I'm gonna skip the mu, yeah, because it doesn't really matter. Okay, so what I was talking about earlier, right, was you can rearrange the four momentum equation into any form you want, get some unknown that you don't like on one side, and then square both sides. Now, in this case, what is the unknown that you don't like? You realize that you know nothing about this outgoing electron. You don't even know its angle. Like, there's some angle here, phi. You don't know anything about it, and you don't want a phi in your expression. So, in this case, it's best to isolate this term and then square both sides. Because once you do it, okay, I think it's better to write down the fundamental first. So, okay, for a photon, this is the momentum, by the way. Yeah. I think this, okay, it might be gone through again in quantum. I'm not, yeah, it should be gone through again in quantum. P3 goes to, okay, then P4, don't care because you don't know. So you put this back here. P4 simply reduces to this because you don't care and it's just always that. Then you have P1 square, which is zero because it's a photon, plus P2 square, which is which is this. P3 square is also zero because it's a photon. And you have 2P1 P2 plus sorry, minus 2P1 P3 minus 2P2 P3. This already cancels out, right? So use so this just reduces to P1 P2 equals to P1 P3 plus P2 P3. Okay. So this is now a matter of working this out slowly. So P1 P2 HMEC over minus HMEC over lambda equals to P1 P3, which is this, plus P2 P3, which is uh oh so why for P1 and P1 squared and P2 squared? It's no for okay for P2 squared it's minus ME squared C squared because that's the electron. But for P1 and P3, they are the photons. So I mean photon mass is zero, so it's just zero. Yeah. Yeah. Okay. Okay, so you can continue working this out. You get this. You can cancel out some factors here. Oh, okay. Okay, so eventually you should be getting this result. Okay. What this is called the quantum scattering formula, which relates the wavelength of the outgoing to the wavelength of the incoming photon. And well, I guess this is not the point of the problem because the point of the problem is not to use form momentum, it is to find momentum and energy separately. But I just did this to show you guys like how much simpler it is to just use form momentum rather than walk through all the slop. Because you realize that in the process of doing this, you never had to find this. And you still got exactly this result where yeah, your quantum wavelength is just given by this. So as a practice, you can try working through momentum and energy separately without form momentum, but I can assure you that form momentum is a very simple method. It's much simpler than doing this. And if possible, if the question permits, try to use form momentum if you can. It just makes your life much simpler. Yeah, that's my general advice for like collision problems in relativity. Anyway, you'll be revisiting quantum scattering in quantum, I'm pretty sure. So if all this is not that clear to you right now, I think we'll walk you guys through this again in the next chapter. Okay. So before I end the class, are there any last questions about special relativity? Okay. Okay, if not, you guys can always just message me. I'll try to get this solutions document done like within the next week so that you guys have time to look at it before S4. Uh, when when is S4 again? Does anyone have, can anyone like just say in the chat? 26 October. Ah, what? 26 October. Wait, what? S4 can't be on a Sunday, right? Okay, 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 I think 24 makes more sense. Okay. Uh, so I guess that's like a bit less than 2 weeks to S4. I would recommend focusing your time on special relativity if you are very confident in your other topics, because again, this is 10 marks that you don't want to throw away. Lah. I can guarantee you that there will be a special relativity question in S4. That's very, very sure. So yeah, yeah, 24 October. Yes. Okay, yeah, all the best for S4. See you guys around next week for quantum. Actually, I won't see you guys, it'll be Monish, but yeah, all the best. Okay, bye bye. Thank you for coming.